lecture, we kind of using the Irwin's model, which derive a plastic zone size. We first derived the plastic zone size from the elastic estimations, which basically just let me put it like this, which basically we found this intersection point give us the radius or diameter of that plastic zone, diameter of that white region. And then we found it's not actually correct. So we derive another, which is more realistic, using the elastic plastic estimation. We found this RP here is just 2 times of R1. Okay, that's because the stress is redistributed after you reach the yielding point. And so essentially our crack length, effective crack length, is the initial crack at the crack tip plus the actual part from the plastic zone. So you can imagine all of that actually is associated with the crack energy release rate. Okay, so that's the effective crack length. It's a bit longer, but still at the same stress. And then in this lecture, we kind of have another model which not thinking of the plastic zone as a circle like here, but thinking the plastic zone more like a strip yield model, which think about the plastic zone in this shade area more like a strip. Okay, so what that means here is a superposition. Okay, let's just shade that. It's a superposition of stress from 2 images. On the right hand side, it's a superposition of one is the original, like is a remote tensile stress you applied on the crack tip. The other one is the local, which is the compressive stress at the crack tip, which give you the kind of shape, the crack shape like this, like a strip. And then this model assumes that shade area is the plastic zone. Okay, so this is basically a principle of superposition of compressive stress and tensile stress. Okay, so what the physical meaning of that is another argument for the plastic zone. And if you look at the estimation of the plastic zone corrections, okay, without corrections, which you assume that is a linear elastic material, which give you the straight line. So what I'm plotting here is, if you look at the stress intensity factor K equal to sigma square root pi A. So basically you divide the whole right term to the left, okay? So for linear elastic behavior, it's just a straight line, give you the value of 1 if you reach the yield stress, okay? So it's just a linear line. Questions? Okay. Oh, you can't hear. I think I didn't mute my audio. Please reconnect. You can leave the session and rejoin the session, and make sure you open your speaker. Okay. And for this part, if you miss something, you go back to the recording and catch that. Can anyone else help me? So if there's nobody can help me, then I can continue. Thank you. Thank you very much. Yeah, excellent. Yeah, okay, that's fine. So let's come back to the slides. So if you consider this straight line is a linear elastic fraction mechanics prediction, but you consider plastic zone correction, which when you plot this k over that term, is no longer linear after you reach the point about stress here equal to about 0.5. Okay, so it started to deviate after that stress. So that going up, that actually the correct correction for the plastic zone effect on your crack tip. So your crack tip will no longer like that linear elastic crack, just easily show a sharp crack. You will end up having something different with a plastic zone, like a blunt crack. Okay, so that kind of region is like a plastic zone shape. So bear in mind here, strip yield model is more suitable for the polymer because that shape, that kind of shape, like a strip shape, is often observed in the fracture of polymer, not for the metal. The metal is more like a circular plastic zone. Okay, so actually that's all estimations. How does actual plastic zone looks like? Okay, look like. So if you look at a simple image, you have a plastic zone circular shape like this. Outside, a bit further of the plastic zone, you get this elastic K-field dominance zone. So in that region, the material haven't reached the yield strength. So it's more like a linear elastic behavior. So let's just show you some actual plastic zone shape. For instance, this image you have seen in my first lecture, you can see this still looks circular, okay? But more likely there's some other shape like a peanut. You can see here like a peanut or 8, okay? The shape like that. Or in far field, they still have this kind of shape, okay? It's like a peanut. So why it looks like that? So let's kind of derive that shape from the knowledge we have learned. So let's go back to the linear elastic material prediction for the mode 1 stress around the crack tip. So for this image, we're still in the Cartesian coordinate system XY. And we have these stress distributions, which in the end will be given the equation like this, which is a function of R and theta. For the stress, you can see any material at this area, you get sigma xx, sigma yy, and tau xy. So which is give you the stress in a kind of arbitrary coordinate system at the crack tip. This part is known from these equations. But to predict the yield of the material, as you remember at the very beginning, we learned that like we need to use the principal stress, which kind of cancel out this kind of rotation term and cancel out the shear stress, so that we get a much simple problem. We just need to look at the principal stress so that we can predict the yield. Okay, so to predict the yielding, the classic criterion we learned is Wall-Mises yield criterion, so which we have this equivalent Wall-Mises stress sigma E, which is the function of the principal stress sigma 1, 2, and 3 for 3D problem. Okay, so so to get sigma 1, 2, and sigma 3 is essentially is the kind of a recap of how to use your like global stress to derive a principal stress. Okay. So I just ask you these questions. Can you remind yourself what is the equation to get the principal stress, as you have done in your coursework as well? So which essentially is using the value calculation from the equation like this. Okay. So that is to find the determinant of the sigma minus lambda I, which essentially will give you 3 eigenvalue, number 1, number 2, and number 3. And you kind of rank these stress so such that you get probably like sigma sigma. Let me just erase that. So well, essentially you will get, you assign that to a group of stress sigma 1, sigma 2, and sigma 3, such that sigma 3 is the largest and sigma 1 is the smallest. So that gives you the, is that right? So I think I did something wrong here. Okay. It's wrong because I always remember we do it the other way around actually, right? So is sigma 1 larger than sigma 2, larger than sigma 3? Okay, that's the correct order. So now let me just clean that. Okay, so you can see the equation for a kind of plane stress condition. Now we forget sigma 3. Sigma 3 is 0 in that calculation. Now sigma 1 and 2 is a function of sigma xx plus sigma yy. So that's the stress which we have already derived from the crack field. Remember that for that crack field. So let's go back one slide. You can see which is here, sigma x, sigma y. And we don't have this term. We have that term in the global stress. Okay, we will cancel it out. In principal stress, there's no shear stress. And then is the function of sigma x, xx, and sigma yy. And shear stress for global stress is here. So that now you will see actually we already get this principal stress. We just need to substitute that into that equation to satisfy that yield criterion. Okay. So essentially, to work out the shape of plastic zones is you get this principal stress once you substitute sigma x, sigma y into that eigenvalue solution, right? And which give you this sigma 1, sigma 2, sigma 3. In the function, as a function, again, of r and theta, because we have this equation related to these two terms, so that once you substitute that into the eigenvalue solutions, you still get these r and theta. And for plane stress, you will find that 0. For plane strain, it's a slight different, but since because we have this relationship sigma 3 equal to the Poisson ratio times sigma 1 plus sigma 2. Okay, that is something I have derived before. So you can watch the lecture note from the previous slides. You get this equation. Just remind you is just write the strain. It's kind of 1 over e. For example, this is epsilon 1 and sigma 1 and there's some Poisson ratio, okay, sigma 2, and the Poisson ratio sigma 3, okay. By rearrange that plane strain, you need to look at epsilon z, which is the out of plane direction. And here, to avoid confusion, you need using x, y, okay, and this is z, okay, because that is in the you can actually use the 1, 2, 3, sorry, but essentially the same. So plane strain, this value equal to 0. So you rearrange that equation, you find you get this, okay. So just that term will give you the sigma 3. So it looks complicated because you have r and theta, these things, but essentially that will help us to find the shape of the plastic zone. So let's look at that. So essentially, we will eventually find the sigma E due to the equation of Wolff-Mises criterion. Okay, that's that kind of things. Okay, square, square, and square. Okay, you just make this term equal to sigma ys, so that you can get the yielding criterion, so that you can get the critical points for the r and theta. Okay, so let's look at that. Okay, so eventually you will find the function r as a function of theta. Okay, so let me just summarize what we have done is, so we first of all we have the stress at the crack tip in a global coordinate system. Then we work out the sigma 1 and sigma 2 as the principal stress. Then we substitute that into this Wolff-Mises criterion. So here you should also get a sigma 3 as well. Then you make this term equal to your yield strength. Okay. Then you will find r as a function of theta, which eventually will give you the term like this. So you find this is kind of a constant, and this is the theta as the variables. Okay, so basically at the crack tip or the material ahead of the crack tip, any position, once you give a theta value, which is a theta is a kind of the angle between the material, small piece of material, the angle between the material with the x-axis, okay, x-axis here, y-axis. So question is coming. Let me come out. Yes, it's already recorded. Okay, someone still cannot help me? Can you confirm those guys who can't help me before and confirm that you can help me now? Okay, thank you. Thank you very much. Yeah, now I'm confident to continue. Okay, so this all lecture is you can find the recording link and you can watch them afterwards. So similarly for plane strain, you get equation just a bit complex with some Poisson ratio term come here. And you find most of the other terms the same. Okay, so by these two equations, now you plot this r. So kind of you get the contour line where the material has reached the yield point. So let's look at that. So at mode 1 opening stress, so you can get this this kind of peanut shape or kind of broad beam shape for the plastic zone. So for the plane strain condition, you get exactly like a peanut shape. For plane stress, because the function is slightly different, you get this kind of broad beam shape. So just remember kind of the shape which you normally see in the experiment and mode 1 loading. Okay, so here I kind of normalize my R by this constant term. That's just constant. So essentially it's just a function of theta. Okay, R is a function of theta, R theta. So you can interpret this curve like all the area inside this contour have reached the yielding point, yield stress. So this part is already in the plastic deformation zone. Outside of the area, you get elastic performance still. So I'm just give an example for the plane strain here. Okay, for plane stress, your elastic zone is outside this area. Okay, so that's interesting. So now we know what looks like a peanut. Okay, and what about in plane shear? So you apply plane shear, in plane shear stress, which is slightly different, but again follow the similar approach by starting from the stress field at the crack tip and mode 2, you will get a slightly different result, and the shape is still like a peanut. Okay, and this too has a difference because still you are apply stress in the plane. So for plane strain and the plane stress, the difference for them is the out of plane contribution. So that will give you different answers here. But if you look at mode 3, which is the out of plane loading, so now you apply like a tear stress, like you tear your paper. So it's the out of plane shear. In that case, the plane stress and plane strain, they are the same because all the stress played here is out of plane. So essentially you will get identical solutions for plane stress and plane strain. Okay, because plane stress and plane strain essentially they have this difference when you look at the in-plane problem, in-plane. However, if you look at the out-plane problem like this one, okay, you get the same solution for them. Okay, so if you get something like a strain hardening behavior like this equation, your stress and strain curve is slightly different with the one we assumed before. We assumed before is like a perfectly plastic. This is the assumed, but more likely you have like a strain hardening go up and up, like this hardening part. Okay, material becomes stronger as you load it, and then this kind of shape will slightly redistribute. So like this dashed line compared to the original shape. This is just extra knowledge. You don't need to know too much of the detail because essentially they are still like the shape. So the dashed line is the original shape, and this kind of a solid line is the stress redistributed. That's why in experiment you are kind of more likely to see this kind of distorted peanut. Okay, now it's more like a butterfly. So butterfly like. Okay, so that's just give you the explanations when you look at the stress or strain field at the surface of the sample during your experiment. So now I wanted to introduce another concept here is triaxiality. I'm not sure I pronounced that right. Triaxiality, yeah, triaxiality. It's a very difficult word for me to pronounce. But anyway, so this word means it's defined as the ratio of hydrostatic stress to the vortices equivalent stress. This is hard to understand at the beginning if you read that. But let me go through that step by step. You can understand more clearly. So it's just triaxiality is just another extreme case compared to uniaxial loading. Okay, think about if you have uniaxial loading, you just apply stress on one direction. But triaxiality is for your local stress, you have stress in three directions, okay? And the magnitude of them is more likely very close to each other. So the extreme case I will show you is hydrostatic stress, where the stress in three directions is the same, okay? So the equation for the definition of this concept, triaxiality, is the hydrostatic stress, the mean stress, which is this one, the mean stress of a principal stress, and divide the vortices equivalent stress, which is this term, for you to determine the yield. And you are familiar with these two terms, right? Hydrostatic stress, it's just the mean stress. And this one is the yield criteria, equivalent vortices stress, which canceled out the kind of hydrostatic contribution, because it's in another word, the distorted stress. Okay, it's basically the shear stress, meaning the shear part. Okay, so let's look at some extreme case. One is hydrostatic loading. So in this case, you will see actually sigma 1 equal to sigma 2 equal to sigma 3. When you substitute this to this criterion, all this term is equal, and they will get 0, 0, and 0. Okay, so the equivalent stress is 0. So when you're going back to this triaxiality, you will find your bottom part is 0. So that means the mean stress, hydrostatic stress, divided by a 0, which give you the infinite value. Okay, so in this extreme case, you have infinite triaxiality. Okay, that's the largest triaxiality you can get. How about the other case? For example, plane stress loading. So in that case, let's assume sigma 1 equal to sigma 2 equal to a given stress, and sigma 3 equal to 0. Okay, so out of plane there's no stress. So in that case, again, you substitute this value to these two equations, and you use the TF definition. TF is a triaxiality, which give you this ratio is 2/3. That means it still has some sort of triaxiality, but much smaller than this case. Okay. And another extreme case, the uniaxial loading, which you have just the stress in one direction, sigma 1, and the other two principal direction is 0. So in that case, you cancel all of the other except this stress in sigma 1. Okay. Now you get this 1/3. So in this case, actually, this is the smallest triaxiality. Okay. So for uniaxial loading, you get the smallest, but smallest still you have a value, a third. Okay, that means you only load the material in one direction. So once you have this concept in mind, So let's move on, and I want to introduce some more knowledge to you. So for a material like a plate, you load it like a edge crack. So if you assume the stress distribution on the surface, okay, just like on the surface, because there's no constraint on the surface, it's just like an open area, and you can think about the remote stress on the edge crack like this, and that give you a plane stress condition just for the surface of the material. Okay. How about if you look at 3D problem? If you look at a region inside the material, like through the thickness, some area like here, okay, it should be a dashed line here, okay, somewhere like this. And you look at, you cut a cross section from here, cut a cross section, and then you view from the top. So your eye is here, okay, your eye is here, and look down, you get this view, which is here. So now you can see the stress in this view. You need to think about the outer plane stress, sigma zz. And sigma xx is the stress along this direction, okay, x. And sigma y is the stress loading in that direction, which we can't see in this cross-section view. But here, I just wanted to emphasize, so within this small amount of material, inside the material, okay, sorry. So that means once you load it, the material try to contract, okay, because there is a Poisson ratio, try to contract in x and z direction. Once you load it in y direction, we load it in y direction. But because of Poisson's ratio, mu, the material will contract in the other two directions, x and z, which is here. Since you have a lot of material surrounded, such that it's kind of bound by the surrounding material, okay? So this constraint will actually cause like a triaxial state of stress of this material inside the material like here. But out of the material, like the surface, you don't have that constraint. So now in this case, you have a triaxial stress. So that means you have stress loaded in 3 directions. So now it's more like triaxiality. So which I mean, if you look at the, okay, the highest triaxiality is inside the material, which, so if you look at the coordinate system, just cut the material in the center. So this is the thickness direction, okay? So basically you cut the material in the center here. You define that is the origin. So you go over here, that's the z from 0 to half of 2b, okay? So that's, now we're plotting the sigma zz along that thickness direction. So which you actually see, obviously, if you're in the surface, that is a plane stress direction. So there's no material to constrain it. So the material have no stress at this point in outer plane, sigma zz equal to 0. That's exactly the plane stress condition. However, if you keep moving from the outside of the material to the center like this, so you're now in a plane strain condition. Now the stress is no longer 0. You get a value, okay, like this. So that is the area where you have high triaxiality, and this the area, there's a transition, like give you A low triaxiality is basically a uniaxial state in that case. Okay, so that's why actually bear that in mind. If you look at the plastic zone in your material, they should have two different shapes. Outside the material is a plane stress. Inside the material is a plane strain. So remember, we have different shape for these two conditions. So you will expect to see that plastic zone will also have different shapes. So which is like this. Okay. So now this is the crack and this is the B. This is the thickness direction. And if you remember, I plot that shape. One is the peanut for plane strain. One is the broad beam shape for the plane stress. So which you can actually see the shape, okay? So outside the surface, at the surface is the broad beam for the plane stress. And inside the material, now you can see actually that the plane strain, the peanut shape for plane strain condition. Another figure which is more clear to show this is like that, okay? So this is just showing you I cut a cross section at the center of the material, somewhere here, okay? So now I can see the plane strain is giving me the peanut shape. Outside is still a broad beam shape. Okay, everyone understand that? Now, there's more things to introduce. Is just to give you the idea. For most people, when they're asked to do some fracture toughness test, they just take a piece of material and go to the lab and do it without thinking whether the dimension is valid for them to do this test. Okay, so for example, I give you a metal material. Okay, and at the beginning you were just thinking, just do a test like edge crack test. But some of the tests will not give you the right answer because the dimension you choose is not valid. Why is that? Because if you choose the metal as a material and do a test like that, you probably will end up your plastic zone size so huge, like that. Okay, that's definitely wrong for you using the method normally valid just doing a KIC test, which is the linear elastic fracture mechanics. But you probably want to do a test which, by choosing a useful dimension, such that you end up you get a plastic zone shape is very confined, just a small region, then linear elastic fracture mechanics can still use. So you can still get a K value. Okay, so let's look at the condition for valid fracture toughness as a linear elastic estimation. So the first condition is for K to be valid, and the specimen must be sufficiently large such that A, this crack length, and W minus A, which is the remaining material from here to here, that's W minus A, must larger than 2.5 times this term. Okay, this term is very similar to the size of plastic zone we estimate is 1 over pi, kind of K over yield stress. Okay, so you can see 2.5, 1 is much larger than this 1.pi. Okay, it's about, this is about 9 times. Okay, so in that case, you can imagine that zone is quite small compared to your specimen size. So you can see, okay, I can use the linear elastic estimation. Another thing, for Kc to be equal to Kic, okay, which Kic most of the time is specifically mean the plane strain fracture toughness. Okay, we must ensure that the thickness B must larger than this term again, right? So the thickness must be sufficiently large so that when you measure the plane strain fracture toughness. Otherwise, you measure the plane stress fracture toughness, which is not the one we normally say for KIC. Okay, I haven't mentioned that before, but now you can kind of bear that in your mind. Good. So just to compare what happens if you have a very thin sample and a very thick sample. What happens for the K value you measured? Just give you some idea why we need to talk about the thickness. So if you look at the thickness, which at the beginning is very thin, like a thin film, and if you increase that, okay, to a point which you reach a kind of a transition point. So at this linear region, it doesn't mean you are actually doing a right fracture test. So let me just put everything out. So number 3, which is this region, it just gives you a shear of failure. Okay, you're more likely not enforcing material at a fracture estimation. It's more like doing a tensile test. And tensile test, you generate enough shear stress. Okay, and then the material will shift. Think about like you don't necessarily need a crack tip for that thin material. You have just no crack, no notch, because the thickness is so thin. Okay, thickness is in this direction. Okay, thickness is in that direction. T, okay, T. It's too small. Like there's just generates much higher shear stress, which give you this fracture like that, or failure, not fracture. And if you keep increasing the thickness, now you are reaching now the K is valid. You get this kind of fracture which associate to the plane stress condition. Okay, that give you a much higher value. Okay, Kc. And you can see when you're closing to the edge area, you still get this shear crack, shear, okay, like that, okay. So if you keep increasing your thickness, now your sample is very thick, and you will see your measured fracture toughness is about half of the plane stress fracture toughness. So that is the value we normally use for engineering material. That is probably have a more safe region to use that value rather than use that value. Okay, so that gives us a much more safe region. Okay, so use a smallest like a critical value, so that we normally the condition for a safe region we use is much lower than here and lower than this critical region. So that's the reason why we need make sure B is larger than that as well. But bear in mind, in our condition is B times 2.5 of this quadratic term. Okay. So let's just look at an example just following this. So a material has a yield strength of 345 megapascal and a plane strain linear elastic fracture toughness of 110 megapascal square root meter. Okay, that's the kind of KIC. So the question is asked us to determine the minimum specimen dimensions BAW, that's the dimension for the specimen, required to perform a valid KIC test on this material. Okay, so we have this condition here, a w minus a larger than this, and this another b is also should larger than this term. So basically we need to calculate this critical term for 2.5 kc sigma y. Okay, now set kc equal to kic, that's the plane strain fracture toughness value. Basically we plug in the value. Now since stress and the kc is all in the megapascal, we can even just use the megapascal here, so they will cancel out. Okay, you can see here, and sigma y is the yield strength, 345. Okay, so that gives you an answer which is in meter. I think it's 2.2, 2.5. I'm not sure that is right, but we will showing you the correct answer in the next slides. Okay, so basically all the term a, w minus a, and b should larger that value. Okay, let me just showing you the correct answer, which is this one. Okay, so a, b, w minus a larger than that, and I don't know a here, so I don't know why he gets this value. Probably a is the 2. This value. Okay, initial a. Okay, so that means the width of the sample, which if I have correct here, the width of the sample is w, need to be like 0.5 meter. That's huge. Okay, imagine that's probably your table, half of your table. That's kind of block of metal will too heavy for you to characterize any mechanic test in your lab. So also you need a very large test machine to do that test. Okay, so in any case, this kind of indicates sometimes when we use this kind of estimation, maybe it gives us a huge number to do, a huge sample to conduct the test. So we can actually, using other method, maybe use a smaller sample and still do the test. Okay, which probably is the reason I introduced the J field for you to understand the problem. J, which is the another term, not G, for nonlinear solid. Okay, plastic material. So imagine that is the large scale yielding sample for metal. So that huge amount of plastic zone like that. Okay, so your G probably is not valid anymore using the linear elastic estimation. Otherwise, you need a huge sample. Okay, so I think we are almost running out of time. So probably next lecture will tell you how to predict the elastic plastic fracture. Okay, there's two methods which I will go through that, which is very interesting. I will go through the British method, okay, which is the crack tip opening displacement when you have this actually blunting region due to the stress redistribution. So the crack tip is no longer sharp; it's become like a shape, a circular shape. So in British engineer just found a very useful method just to measure that displacement. Okay, you can measure that directly from the experiment. Looks very easy actually. And American scientist, okay, from Harvard, actually derive another more kind of from mathematical point of view, which is called J contour integral, which basically you imagine there's a crack like this, blunted crack like this, and you have a line like this dashed line, and goes through this crack tip. Okay, they found actually they can integrate this whole curve as a boundary. We'll get you a J, which is the energy release rate for nonlinear solid. It's again, if you from energy method, which is minus delta potential energy over delta crack surface area. Okay, so both of them actually is equal. They will essentially will find J is equal to delta times sigma yield strength. Very simple equation to relate these two. Okay, so you can use both of the way to predict elastic plastic fracture.